So in my last talk, I discussed how to actually present and test evolutionary computing techniques or meta-heuristics in general. Today, I'm going to talk on a recently proposed and very effective version of meta-heuristic that is called spherical search optimization. Of course, this is a mathematical and kind of dry name compared to other very interesting names. And the name comes from the geometry of the search locus of different population members under this algorithm. I think one of you need to mute. There is a lot of noise I can hear. I can hear a lot of noise. Now I think it's fine. So you see, the name itself is derived from the geometric locus that is followed by the population members under this algorithm. That's why it's simply called spherical search. And it's a mathematically inspired algorithm, inspired by linear algebra, in fact. No inspiration comes from nature, except for the evolutionary framework itself. So I'll tell you what the algorithm is all about and how this philosophy could be incorporated into other algorithms. So in the beginning slide, you can see my email ID. If you require any sort of reference, although the codes and other things about this particular algorithm are all in public domain, but still if you require any reference or any clarity about the codes and data, you can directly drop me an email at this site. So let us begin. As we once again know, let us just recapitulate that if our optimization problem is non-convex, non-linear, continuous. Continuous means the search variables are actually real numbers. And the real numbers can have any floating point value. In fact, computers cannot represent real numbers very clearly because their memory are finite. Nowadays, we have very high precision machines, and that's why we can still store, manipulate, and process real numbers whose differences are very small. In fact, in case of any such digital system like a computer's memory, if the difference between two numbers fall below certain delta, the computer assumes them to be same. We will be discussing continuous or real parameter optimization with respect to actually such granular setup in a computer. But anyway, the general problem is you have a function, scalar function f of a vector variable capital X. Capital X can range from there are certain upper and lower bounds for each component of capital X. These variables that constitute the vector capital X are called the decision variables of our problem. You can have additional restrictions imposed on the search space in the form of inequality and equality constraints. And your function is, of course, non-convex. Non-convex means you cannot afford the luxury of using derivatives, or even you may not have a functional form, mathematical functional form at all. That comes to the black box scenario. Gradients are not available or not useful. That's why most of the gradient-based optimization techniques will not apply. The problem domain-specific knowledge could be used only within a black box. So the function is like a black box. Like if I ask you what is the temperature of the room you are sitting, that's a function of the number of ACs on, the relative humidity, maybe how many windows are open, how many people are sitting in the room. But if I ask you how exactly that dependence manifests itself, you cannot put it in the form of a single mathematical equation. So you can only measure the X and you can only measure the Fx. Fx may be the temperature of the room. So you will deploy different sensors for them. But how X translates into Fx, you don't know that. That is called black box scenario. Meta-heuristic optimization algorithms are the simulation-driven, population-based stochastic techniques which have been tailor-made for solving such optimization problems. The word solving might be too strong. We should say they are used to, attain an acceptable solution within certain range of precision, which is a approximate optimum. So, how tough this problem is, I have some question for you. By the way, am I clearly audible to all of you? Hello. Sometimes I will ask you.
Yes, sir.
Very good. So this you have been, I am sure you have been listening lectures on many other so-called nature-inspired techniques for so many days. But have you ever thought, how tough this problem really is? Continuous real parameter optimization. We are not talking about, at least in this lecture, I'm not going to discrete optimization problems where decision variables can take binary values or integer values. I'm not going there. Think of a function. Suppose you have a function f of x1, x2, and x, and this function x1, x2, and x3 are just Boolean variables or binary variables. So you have to employ an exhaustive search to find out the maximum value of the function f. So you list out the values of x1, x2, and x3 versus the value of the function f. 0, 0, 0, what's the value of f? 0, 0, 1, what is the value of f? This way you can list out a finite number of all possible combinations of the three binary variables. You can make an exhaustive comparison of them and pick up the biggest function value and the corresponding combination. This is called exhaustive search because you didn't spare any possible answer. You have checked all of them. So how many comparisons you have to make for this? 3 variables. Suppose you have only 3 variables. So how many comparisons? That's a question for you. Hello, am I audible?
Yes, sir.
So could you please answer? 3 variables, exhaustive search, how many comparisons? This is very easy. How many rows will be there in the truth table? There are 3 Boolean variables. What is the answer? I understand that in the online mode, the answers, getting answers from the audience is a very big thing in the day. So let me tell you, that would be 2 to the power 3 or 8. Only 8 comparisons, you exhaust all possible solutions. But if you have 1,000 Boolean variables, x1, x2, x3, x4, up to x,000, and your function is a function of 1,000 Boolean variables, not really a big one, and this is a very pertinent problem. In fact, if you try to solve the feature selection problem for classification by using an evolutionary or swarm algorithm, you will have to create a binary variable, a binary split string of zeros and ones. If a bit is 1, that means that corresponding feature is considered. If the bit is 0, that means that feature has been discarded. So if you have d equal to 1,000, then of course you will have to do 2 to the power 1,000 comparisons for the exhaustive search. Suppose you have a computer which can do 1,024 such comparisons in 1 second. Not very bad computer. This computer can generate 1,024 such 1,000-dimensional bit strings, evaluate the function at all these bit strings, and give you that. This takes a time of 1 second. 1,024 is 2 to the power 10. So this computer will take 2 to the power 990 seconds to solve this problem through exhaustive search. Nothing will be required, no algorithm, no special tailor-made things. Exhaustive search means it will evaluate all possible solutions and tell you the exact bit combinations for which f of x will be maximum. So how much time it's going to take? How big is 2 to the power 990 seconds? How much time will an ordinary PC? This is the situation. So this is once again a quiz for you. How big is 2 to the power 990 seconds? In days, weeks, years, etc. Because we have to express it in layman's language. Common people will understand. 2 to the power 990 second is too big or too small? What do you think? So you see, if I try to employ a common computer science-based exhaustive search method or just count the number of comparisons for this simple situation, where my variables are Boolean variables, they can be zeros or one. I have 1,000 Boolean variables. So it takes a time of 2 to the power 990 seconds by a ordinary PC. If you have a supercomputing type machine, it can this time can get down to maybe 2 to the power 800 or 850 seconds. Doesn't matter, because from the day of Big Bang, when the universe started till today, the age of the universe is of the order of 2 to the power 700 seconds. So you see, the time that will be taken would be much greater than the age of your universe. So this is called an intractable problem. Of course, if your variables are not just Boolean, but they can be any real number, you could imagine the situation. How much time it's gonna take. That will simply blow you up. So real parameter optimization problems are really hard. That's why, as a shortcut or as an intelligent search, intelligent optimization, machine intelligence, artificial intelligence, you have heard of so many things. What's that? That is kind of a wormhole which could avoid the need for exhaustive search and still get you down to a very nice and very acceptable answer. That is what these meta-heuristic type algorithms are supposed to do. And real parameter optimizers come from so many different diverse domains of science and technology. As I was saying earlier also, we collected problems from diverse domains to prepare this competition under IEEE 2011. And all of them boil down to there is a function f of x. X is a vector of real number. You need to find such a value of the vector x for which f of x happens is globally minimal or globally maximal. In fact, these two are just the opposite faces of the same coin. If you try to minimize effect, that means you are trying to maximize minus of that vice versa. An example problem formulation. Suppose we have a prototype 2D IIR filter design problem by optimization. So this is our prototype for the filter called a Butterworth type prototype. And we will simply take the Z transform, that means the discrete, it's a version of discrete Fourier transform. So in the Z domain, we have a grid of, this is two-dimensional because this is applicable to images, image denoising. So we'll have a grid of size n1 into n2 as you can see here, and we will just sample the response of the original system from these grid points, and we will also see what is the user specification at these grid points. That is the desired response. So basically, we will form a difference between the desired and the actual response, put it in square form because we are just interested in where these are mismatching, and then we sum that up. The solution could be represented in this manner. So this is a vector. This vector contains, for a two-order, second-order system, this capital N is the order of your filter. So for a second-order system, this vector contains all parameters in this transfer function. All parameters in the transfer function. Now you will use such a vector as the particle in particle swarm optimization, or a cuckoo's egg in cuckoo search, or you will call it a flower for some versions of artificial bee colony algorithm. You can call it an intelligent water drop, so many different things. But at the crux, you will evolve, you will take up a set of such possible vector sets and you will go on changing them in an iterative manner. You will go on refining them in an iterative manner until you approach such an X for which this mismatch between this is our objective function or cost function. So this mismatch becomes minimal. So that is a solution representation mechanism for meta heuristics. Just an example. For real parameter optimization, a meta heuristic is a heuristic method for solving a very general class of computational problems, all of which here in my talk, they are all sharing a common scenario. They are all real parameter optimization problems. And the meta heuristics combine the user given black box procedures, and the name combines two things. One is the Greek prefix meta. Meta means beyond, here in the sense of a higher level. And then there is another word, heuristic. The word heuristic comes from the Latin word heuristicum, which means to find. This chart shows you some of the meta heuristics under different categorization, but of course, every day some new algorithm is being proposed, at least every week, I am sure. So not really possible to keep track of all of them. All of them are not also very important. But this green portion is naturally inspired from either Darwinian evolution or the foraging behavior. Foraging means searching for food. So the foraging behavior of a school of fish or flock of birds, collective intelligence exhibited by social creatures, that comes under this side, particle swarm, ant colony, and so on. And on this side, we have local search-based methods, trajectory-based methods. These are different types of methods. Population-based methods are here. Local search methods are usually applied to individual, just one single solution which is locally iterated. That's why that doesn't fall into population-based methods, but they can have some overlap. The overlap we have estimation of distribution algorithm and so on. So what do we exactly mean by meta heuristics? How does a single agent find a global optima if the function is continuous, nicely differentiable? You start somewhere here. This is the position of a trial solution, and you jump along the negative gradient direction, which the gradient looks like a tangent to the functional surface. At least it's a projection of the tangent for sure. And at the next n+1 iteration, you have taken a jump along the negative gradient direction, minus of grad of f direction. The jump step size is new. So the solution moves along this direction, then from where it has come down, it will take another jump along the negative gradient direction, and this will continue until you reach the minimum where the gradient vanishes and you are trapped there forever. But what will happen to this multimodal, noisy, and discontinuous function, which could have even noise in the landscape? There are multiple valleys and peaks, and they can be non-differentiable. For such problems, the idea is the multi-agent optimization in continuous space. It's like you have a hilly landscape, and there is a team of trekkers, each of whom has some limited communication with the fellow teammates, and these team of trekkers have to spread around that hilly landscape. They have to, find out. They have to detect the highest peak or the deepest valley in that hilly landscape. These agents are basically the trial solutions, possible candidate solutions of the problem, and their locations could be perturbed or changed over time. They are scattered on this hilly, mountainous landscape that's called alpine function landscape. And we expect that they follow certain search states and they will adjust their locations in such a manner that after some time, if this situation is achieved, then we say our algorithm has converged. So this is what should happen during the convergence. This is what usually happens during the convergence. The best solution reaches the peak and the other solutions remain scattered around the best solution. Now, as we see, the main task of a search operator, every meta-heuristic algorithm comes with search operators. For example, in particle swarm optimization, I'm sure most of you have been, at least if you are not now, you are familiar with what is particle swarm optimization. So, for example, when it comes to PSO, the velocity update is basically a search mechanism. When it comes to genetic algorithm, the mutation mechanisms for real coded GAs, there are various mutations which are actually processed to perturb the solution. So the main task of the search operator is to find the feasible region if there are additional constraints, gradually minimize or maximize the objective function value, maintain population diversity and convergence, avoid trapping in local minima, and provide the proper balance between two aspects of meta-heuristic search. One is called exploitation and the other one is called exploration. I'm sure you have heard of these two words so many times during this workshop. Exploration is about diversification. Just spread your solution points to diverse areas of the landscape. Feasible search volume. And exploitation is can you intensify the search in a small basin of attraction surrounding some solution point? And intensification means more agents will come to that region. They will have a detailed search. Okay. Detailed search, hairbrush search, comb search, so that they do not miss the optimal point which might be there in that basin. And evolutionary computing, the success of such meta heuristics depend upon striking a proper balance between these two tendencies: spread out and converge. These are the two tendencies: exploration and exploitation. To generalize the search trajectory of the most prominent algorithms, let's take two main algorithmic frameworks, which, according to me, are the two most fundamental algorithmic areas in real parameter optimization. In discrete parameter optimization, genetic algorithm and ant colony, they are two very, very prominent paradigms and very original. All the others are just some permutation combination of these type of algorithms in some sense. So let's look at the two main algorithmic frameworks. In PSO, what happens is a solution is updated by using its inertial component VIK, attraction towards the personal based solution, which is like PIK. This is I is the particle index. PI is the so far encountered best location by the particle, and the current location has an attraction term towards this PI. Also, it is attracted by the global base, which is, or the neighborhood base, which is the best point discovered so far by the entire swarm or by some neighborhood of it. So this is how we just the velocity is a sum of these three components. Velocity is basically balancing between the tendency to fly in the original direction due to inertia, to get attracted towards the personal based location, and to get attracted towards the global based location. And the next position is simply this updated velocity plus the older position. This is PSO. In DE, differential evolution, what happens is every population member, every randomly selected. So when we perturb a population member, when we create a mutated variant of a population member. Mutation is just another name for perturbation. So for each xi, we randomly select, this is one particular D mutation, D has multiple types of. So for each member, we randomly select 3 other population members. We take the difference between 2 of them, scale the difference with a scalar number f, and add it to the third member of the population. So you see, if you are picking up XR2 and XR3, perturb xi, you take this difference vector according to the triangle law of vectors. This is the difference vector. You scale it with f. If you scale it with a scalar number f, its direction remains all the same, and then you add it with the third vector xr3, sorry, xr1. So now you create a new solution point. This solution point is called donor vector or mutant vector, vi, corresponding to xi. Capital G is the generation index. So now we have to determine whether vi will survive or xi will survive, or maybe both will be mixed together to form a new solution vector ui. That's what we done. The majority of the algorithms utilize similar search operators to update the population. Most of the algorithms use some kind of scaling and combination of the existing solutions in the existing group, existing population, to form the new candidate solution, except for the distribution based ones which try to modulate or improvise the underlying estimated distribution from where the algorithm, the population has been sampled. Example of such distribution-based methods are, of course, estimation of distribution algorithm or EDA, and some versions of CMAES also, like evolution strategies also. We are not going to discuss those things here. We, on the contrary, are going to focus on the first type, a very general form of, the offspring generation process. Offspring means the perturbed points. You started with a set of solutions. Now you perturb each of them, generate a new set of solutions. Then you decide who will survive for the next level of perturbation. That's the general framework of any meta-heuristic. So a very general form of the offspring generation process aided with the search operators could be written like x is equal to r plus sum over tk Hadamard product fk sk. What are these? X is the new offspring. So we are trying to, there are various types of equations involved in different algorithms under different names. We are trying to present a unified view here. X is the offspring produced, R, SK, and PK are the parents participated in the process. PI is the parameter of the search operator. For example, the tape size parameter or the scaling factor in differential evolution. Small fk is the kth mutation function of the search operator. N is the total number of mutation functions participating in the search operator. We call them mutation function because they are the perturbation state. And this symbol, one of you need to mute, I think. There is some noise. If you have a question, that's fine. Otherwise, please mute. Hello? I can hear some noise. Not sure where from this coming. Hello? Can you hear me? Can you hear the noise? Now, big noise. Okay. So I think now the noise has gone. So as I am saying, as we were discussing, this is a very compact representation of the solution generation process for most of the meta-heuristic. And you see, ESO and D fit to the framework of this equation. Uik plus 1, which is the current solution, which is the current offspring, is simply like xik plus w times w is a vector and Hadamard product. This symbol means Hadamard product, which is basically a component-wise or entry-wise product between the two vectors. So if we go for such Hadamard product, you will see that the equation of differential evolution nicely fits into it. Also the PSO. In case of the first one is for PSO and the second one is for DE. And for other popular algorithms, we are just showing 5 very popular methods: PSO, DE, ABC for artificial bee colony algorithm, TLBO for teaching learning based optimization, which is essentially some variant of PSO. And then we also have this GW, Gray-Wolf optimization. So when we have these type of algorithms, all these algorithms at the base would be represented in that particular form through these equations that we have just shown. So, and there are some special terms written here, which are like how the individuals are selected. What is this R? Previously, you have seen an R over here. This R is the offspring. So offspring itself or random. These are the choices. FOD stands for the functional form. Everywhere, if you look at this function fk, everywhere we are representing this function as if just the first order difference. That's why it's FOD. pk is the parameter associated with the algorithm, which could have a uniform, which could be sampled for uniform distribution or constant or linear function. These are the things. GISM, designated individual selection method. ISM, Murray-Wheel selection method. SI, selection of individuals. So under selection of individual, you see, we can have this sort of methods for selection of the individuals. We can add this sort of methods with the selection of the different offspring. So, as shown in these equations, vector sum, vector difference, and vector scaling are involved in the mathematical model of the search operator. All these search operators, we have just taken 2 examples here of PSO and DE, and we have proposed 5, just shown 5 of the other algorithms which fit to this particular framework. The vectors, so all these equations, they are using the vector sum, the vector difference, and the vector scalings involved in the mathematical model of the search operator. You see, if your original solution point is at x1, x2, for different choices of your search operators used in PSO and DE, the perturbed point will be located inside this square, because the perturbed point will be within certain maximum and minimum values between, let's say we are just clipping it at 0, so it will be confined within the if your pk times fk, this summation is negative, it will take a negative value, otherwise it will take a positive value. So YIA is the minimal value of the part of the solution points, perturbed solution points, and YIB is the maximum value of the perturbed solution points. But if you carefully notice for the earlier slide, especially PSO-D type algorithms, this point x1, x2 is geometrically within this black cube. It cannot go beyond the black cube. That is why black square in this case, in 3 dimensions, it would have been a cube. That's why we say PSO, DE, etc. This sort of usually very popular algorithms actually impose a hypercubic search, HC style search, which has been shown here. they impose a hypercubic style search. In some special cases, so this is just for, we are assuming that we have only two first order difference operations here, only one first order difference operation here. In some special cases, the locus of x here essentially means the entire region in which x can be, the entire area which could be spanned by x or swept out by x. So in some special cases, the locus of x would be the D polytope space. So D polytope space stands for union of hyperrectangular or hypercubic spaces. So if you, especially when you use multiple difference vectors, like in PSO we are using two difference operators, for such cases, the locus of x in the two-dimensional search space would be like this. And discrete values of pk can create disconnected D polytope spaces as the locus of x of the search space. This is basically the reason why most of the meta-heuristic adopt the hypercubic search style in their optimization process. Every individual that is being perturbed will remain confined within a hypercubic region, okay? Within a hypercubic region, or within a polytope type region like. Now, can we use, our question was, instead of such hypercubic regions which have very non-smooth geometry, of course, it's not as smooth as sphere. Sphere is one of the most flawless shape because it doesn't have any corner. We all know that, right? So several works have been reported in the literature where the algorithms try to adopt hyper-spherical search style. Any development cannot jump from the sky. Every development in good science actually have a continuity from the earlier development. So if somebody claims I have observed nature today and tomorrow I come up with a groundbreaking algorithm, there is sufficient reason to doubt such claims. Because developments are always, very slow and very continuous. In here, earlier people have tried to seek an answer for this question. Spherical search style, hyperspherical search style, can we adopt that? In 2009, more than I think 12 years ago, Sabat and Flack-Ali, they proposed an hyperspherical operator for the PSO, and it was published in the Applied Soft Computing Journal. So what they did is they took up a variant of PSO where the positions of the particles were transformed from Cartesian coordinate system to the hyperspherical coordinate system. And in hyperspherical, this is essentially the polar coordinate system. So one coordinate surface is what? It is a surface along which the value, one of the coordinates remain constant. So if you see polar coordinate system, r, theta, phi, if you suppose r is constant, so in that case, you end up with a spherical surface. So in order to advocate hyperspherical search trajectories, what these people did was they converted the positions of the particles into polar coordinate system, and then the operators of PSO were applied. Evidently, it is possible by transforming the coordinate system, we can change the locus from HC stands for hypercubic, to HS. A similar concept was utilized. So you see, there was another paper, although much later in 2019, which uses spherical evolution for solving continuous optimization problems by other people. So what they did is, so They integrated the hyperspherical search in the framework of differential evolution, and the resulting algorithm was called spherical evolution, or AC. So in AC, RAND B is similar to D, but they are using something like they are using a kind of coordinate transformation for achieving. Spherical search optimizer, SSO, which is done by some other people, but they share a very similar name to the algorithm I will be talking about. This was also published, I think, in Neural Computing and Applications in 2019. They adopted the HS style search for up to 3 dimensions of the search space. And for higher dimensions, the process of HS type search was not defined. So the above examples indicate that the hyperspherical search style could be very promising concerning the hypercubic search style, in contrast to the hypercubic search style. So HS, the search style of the such hyperspherical locus of the solutions are very much attractive because of 2 reasons. One is HS renders more population diversity during the search, as the volume covered by the locus of its search style, or by the locus of the optimizing agents, is much more than that covered by the HC locus. This is why HS can better tackle premature convergence because it has more diversity. When we are converging to a false optima, when we are converging prematurely, all our solutions will quickly get trapped into a local basin of attraction, and they may not be able to jump out from there. This could be avoided if right from the beginning we could maintain a good level of population diversity. The solutions remain enough separated. HS is also rotationally invariant, as the locus of the HS style search is kind of independent of the coordinate axis of the search space. So rotational invariance is a very big thing. If your coordinate system rotates, and if that affects the distribution of the new solutions created by your evolutionary algorithm, then probably the problem is if your function is a rotated function, if it has strong epispaces or linkage among its decision variables, then your algorithm will be very poor choice for optimizing those sort of functions. That is why rotational invariance is very important. Although preserving more population diversity helps algorithms to avoid premature convergence, the convergence rate can then slow down. If your algorithm is only focusing on maintain a very high population diversity, then the convergence rate can greatly slow down. So for striking a proper balance between convergence and population diversity, HS search style with a little modification would be very important. This is where we are going. See, in any evolutionary search, the mutation operators, usually which are perturbing the solutions, that's like more like you are giving a jerk to the search space and the solutions are as if jumping from their old locations, creating new copies at different locations. These are the perturbed solutions or mutants. So mutation or similar perturbation operation increases population diversity. On the other hand, selection, when you are selecting, you are always picking up the best solutions. So what you are doing is you are narrowing down the spread of the population into some promising region of the search space. So selection enhances exploitative search. Now coming to transformation from HC to HS, if you look at these two, once again, let's see the PSO and DE basic steps. So this is the PSO and this is the DE. And C is basically uh, the This is a very simple D. We have avoided the scale factor. In case of scale factor, if you have scale factor, then C would be something different. So the final solution after crossover is this one. If C is, so this essentially means Ui is such a vector whose first component, whose every component can be either xi or the corresponding component of xi or that from vi. Why is it so? Because if this random number is less than equal to CR is the crossover rate of D, then that Sj is 1. If Sj is 1, then this is like x plus b minus x, that is v, because that component of C is 1. Otherwise, if Sj is 0, then it is simply x. So it's a combined expression. Now, these solution update equations can be represented using three elements: vectors, diagonal matrices, and coefficients. So we can both the two equations from two very different meta heuristics. We can represent them in a single manner. This is a single expression for the two equations, where R is the resultant vector, M and N denotes indices. This should be denote, actually, it's a typo. Alpha I is the ith coefficient. Wj is the diagonal matrix of real numbers yi, and Zj denote the two vectors. Two vectors means two perturbation vectors used inside the perturbation term. So the HC search style of this algorithm can be transformed into an HS search style. There can be two ways. One is change the coordinate system of the search every time. So you can go to a polar coordinates or something like that. That is what is done every time. Or you can use a projection matrix. The projection matrix is a matrix which, when multiplies a vector, it projects the vector onto its typical plane. And by projecting the same vector onto different planes, you can have a spherical coordinate system for the locus of the vector. That is the idea of projection matrix. So when it comes to projection matrix, we can use such a matrix, and projection matrix is also idempotent. So if you have gone through some basic course on linear algebra, you should know that if P is a projection matrix, then P square is equal to P. P, and therefore all the other powers of P are also equal to P. Anyway, so now we can convert the hypercubic search style to hyperspherical search style by transforming the equation by using the projection matrix technique. That is exactly what spherical search does. And these two are the two papers on spherical search, very recent papers, where this algorithm has just been proposed. And now the use of the algorithm is gradually increasing because it is really very easy. So when we transform, we can change the coordinate system of the search space by using a B, which is an orthogonal matrix. We know an orthogonal matrix is a matrix whose transform is its inverse. So, sorry, whose transpose is its inverse. So if B is an orthogonal matrix, then B transpose is actually I, or identity matrix. And then we can have nice, projection properties from this BWJ B transpose ZJ. So this portion could be written as a projection matrix. So this is one. When we have the orthogonal matrix comprising of the current basis of your vector space, then you have this sort of coordinate rotation. On the other hand, if you do not want to use the orthogonal matrix, And it's also better to use a projection matrix P. P is the projection matrix. And when you use P, then your transformed system looks like this. Here we are showing the locus of, so the entire region which could be covered when you perturb the vector 1 and 1 transpose by using these two methods. See, the first term remains same in the coordinate system change because that's the reference point. The second term is affected, the second set of perturbing vectors are affected. What is happening is, once again, should be very sure. You are creating an offspring vector in the same plane where there are these x1, x2, x3, or maybe the local based, personal based. You are creating them when you are using the linear combinations and other things, you are creating them on the same plane. But then in hyperspherical search, you are trying to also perturb this vector in such a manner that they get out of that same plane and they can be in any plane. That perturbation is given here and here. That perturbation comes through the projection matrix. So the idea is, if we perturb the vector in that way, it can cover much more area around the single solution point which could be obtained originally. That's why we are trying to perturb, right? So, and if you see, this is the original 1,1 point. If you perturb it with this projection matrix, you get the locus is the whole circle. And if you perturb it with this term, the locus is only a part of this particular quadrant, or the first quadrant. So if you apply such projection-based operators on the DE, all other things are like D, just this spherical projection-based operator is used in D, then you get this sort of trajectories, or this sort of locus, these green dashed circles, instead of such pointed and cubic locus. So there comes the spherical search algorithm. Spherical search is a derivative-free population-based meta-heuristic for global optimization problem. In spherical search, the algorithm's framework is utilizing a hyperspherical search style for generating the new solutions. That means possible new solutions create hyperspherical subspaces in the search space. This framework provides a better balance between the convergence rate and the population diversity than other HS search style based algorithms. Thus, the performance of SS is better than other HS style search algorithms on the bound constraint optimization problem. So you see, in the first paper, SS is applied to a wide variety of bound constraint real world problems, and the performance of the algorithm remained very competitive against the existing state of the art. If you look at the second paper, which was published in the GECO 2020 conference, the algorithm took part in the special session and competition on real world single objective constraint optimization problems under IEEE WCCI 2020. WCCI stands for the World Congress on Computational Intelligence, and GECO is also very prestigious, the Genetic and Evolutionary Computing Conference. So the algorithm took part in these two competitions before we made it announced to the rest of the world, and over a set of 57 real-world constraint optimization problems, SS secured the top rank in this competition. So this is the framework of SS. This is SS in a nutshell. Start with an initialized population. The population size could be just same as PSO, 40, 50, something like that. And there are three parameters, in fact. Calculate the search direction, calculate the projection matrix, calculate the trial solution. Now select the trial solution through some selection mechanism, and check the stopping criteria, and then reiterate. That's the thing. So we have a set of solutions. We are simply perturbing them, and we are also projecting them to different planes that creates the hyperspherical search style. This way, new solutions are born. Then we are making a selection between the new and old solutions. So the step one is, first of all, we randomly initialize population P within the search space from the uniform distribution. This first equation tells you that the jth component of the ith solution vector is a randomly chosen number between a given upper bound and a given lower bound. These upper and lower bounds are fixed from a coarse knowledge or approximate knowledge of the problem at hand. And we just pick up any number between the designated upper and lower bounds uniformly, randomly, and put it there. Step 2 is we generate a random orthogonal matrix A by using Gram-Smith orthogonalization. We calculate a binary diagonal matrix Bi of size C cross C. So once we generate each solution vector, now what we do, we generate a random orthogonal matrix. Any orthogonal matrix has its columns orthogonal to each other. So if you take the dot product of two columns of an orthogonal matrix, that dot product will become 0. You can pick up a random matrix of a designated D cross D size, and you go on, D is the dimensions of your problem, D is the number of decision variables. And you can go on using Gram-Smith orthogonalization technique or Given's rotation. These are numerical techniques from linear algebra, using which you can orthogonalize your matrix. So that is A. Now we calculate another binary diagonal matrix Bi of size E cross E. And this matrix has a rank Ri if in the diagonal vector there are Ri 1s and D minus Ri 0s consecutive. So this Ri is the diagonal, is controlling the rank of the diagonal matrix, and it is usually an integer from the range 1 to D. So now what we do is, for towards rand method, the following equation is defined for calculating Zi. There are two versions of spherical search initially. One is towards rand. In towards rand, what we do is, suppose for the ith solution vector, we first calculate a direction Zi. How do we do that? We randomly choose three other solution vectors with indices Pi, Qi, and Ri from the entire population, such that they are distinct from each other. And we form a combination like this: xpi plus xqi minus xri. Then we take a difference from our current solution vector itself. So it is as if the current solution vector is directed towards a random point generated by these three vectors, which are randomly chosen from the population. On the other hand, in towards best method, we use the following equation, this equation for generation of the direction Zi. Zi is a direction vector. Here, PBI is the randomly chosen solution among the top P solutions searched so far. So P becomes another parameter. If you have 100 solutions and P is 0.1, 10% maybe, that means this PBI will be the one of the top 10 solutions in the population. Finally, after we have chosen this Zi, we can create the random trial solutions. These are our perturbed solutions, Yi, by using Xi plus Ci times, Ci is the step size. This is essentially the projection matrix, which is in the form of A times B times A transpose. B is the diagonal matrix. And So A times B times A transpose. A and A is an orthogonal matrix, B is a diagonal matrix. That means this is much in the form of a eigen decomposition. And the rank of BI, the middle matrix, actually controls the rank of the whole projection matrix. So, and to create the population for the next iteration, the selection of the solutions are performed by this equation. This is simple one-point competition. In the next iteration, we just see if xi is better or yi is better. The original solution was xi. If xi is better, what is meant by better? For the minimization problem, we see if f of xi is less than f of yi. If it is, then we select xi as our xik plus 1 or the new solution, or we select yi. Okay? So this is the simple mechanism of spherical search, and this is just an illustration of how the locus of yi. So if your xi is here, actually the step size parameter denotes the diameter of the circle, and if you want to get your xi at other positions, if you want to project your xi onto other planes and other positions, you need to use this sort of a transformation, c times p times zi. Let's take an example, hand tracing of the algorithm. Consider a two-dimensional function f of x comma y, which is x square plus y square. And the minimum is where? The minimum is at 0, 0. We can start with a population of 5 candidate solutions randomly initiated in the range minus 10 to 10. So these are the 5 candidate solutions, as you can see. And you see the solutions are not close to 0. So we can compute the search directions as per the equations, either towards rand or towards base, something like that. At r equal to 0.3, C is this one. Set of, so we have 5 solutions, so we have 5 step sizes, and this is the A matrix. This is an orthogonal matrix. So we get these y values after using this spherical search equation. We're using this equation. And we see that after comparing the trial solution and the old solution, solutions 3, 4, and 5 are updated for sphere function. So at the end of first iteration, the best solution found was 1 and 3.32. And then as we move more, the series of convergence is like this. I mean, initially we started with this value, 12.04, best solution, then 10.92, then 2.47, and so on. So you see the value is steadily decreasing until we reach 0.0. At the end of 8 iterations, we have very close to optimum, 0.02 and 0.00. Now we can visualize this behavior in the form of a video also, how the different solutions and their spherical trajectories could be generated. Spherical trajectory is actually generated via this projection operation, slightly different from normal projections. If you look at this video, it shows you this is the sphere functions, search behavior of SS on the sphere function. These green points are the newly generated points. Please try to understand. I'll just start. So initially you have only the blue points, and then gradually the green points are being developed. Then the spherical, along the spherical trajectory, new points are developed, and the selection mechanism is taking place. Gradually it is converging towards the central portion of the search landscape. until most of the points just converge. That's the convergence. Okay. So you see the spheres are also gradually reducing in size because of the small step size parameter and damping. So I hope we are almost at the end. So finally, you see everything converges here. That's a complete convergence. Coming to, okay, yeah. So this is for the Raspbigin's function. Raspbigin is a very much multimodal function, and it has multiple local minima and multiple global minima also. You can see these are the global minima. And it's multimodal because center of each of these are the global, one of the local minima could be found. And let us see how spherical search is distributedly converging to multiple minima simultaneously. Some points will come to global minima, some points will come to local minima. And in fact, when we have a niching-like situation, niching means multimodal optimization, it is better to have more than one global minima. It's better to detect more than one global minima at a single go. So if we do that, then it does mean that we can very easily switch one optima as required. In multimodal, there is a rich literature on that is called multi-peak and multimodal optimization or niching. In niching, we exactly do this. So you see, gradually the solutions are entering into these different search. These are the small optimal basins. Each of these round sectors, these are the constant cost contours of the function I was talking about in the last lecture. So different solutions are entering into different such loci, different such basin of attraction. This is the global basin at the intersection of 0 and 0. It's already converged. But since the solutions are diversified into different optima, still some new solutions are being born. So, if you see, this is how this is called basin to basin transfer and contour mapping property, how the solutions are actually moving into different optimal basins of attraction and gradually converging over there. This is what is happening in Raspbigin's function. So I just got rid of those cyclical sectors, and if you run the code, this is actually what is happening. Nice distributed convergence. Many solutions are there at multiple peaks. So if you just look at after the population has converged, if you look at the location of these solutions, and if you look at the solution vectors, then you know what are the local optima and what are the global optima of the function. You can compare their functional values and you can get nearly all global optima. In fact, these blue ones are the global optima and these yellow ones are the local optima. So you see most of the global optimas have been discovered. The color is proportional to the heat map type contour plot. The color is proportional to the value of the function at this point. And I showed that how starting from scratch, initially all the solutions were disparate, then how they are converging mostly to the global optima. So that is the end situation once again. If we try to see the convergence behavior, then we have only two dimensions. This bold black one, continuous black one is for SS. We are plotting the best objective function value in logarithmic scale versus the number of function evaluations. This is a logarithmic scale, the y-axis in logarithmic scale. So if we do that, what do you see? SS is not that good for two-dimensional problems because PSO and D are quickly decreasing the function value. If we increase the number of dimensions, in fact, at higher dimensions, the projection matrix properties become more prominent, and at higher dimension, projecting each such direction Zi to different planes is more important than in lower dimension. That's why if you switch to 20 dimensions, now you can see how steadily the functional curve is decreasing for differential for the spherical search optimizer. So you see spherical search is decreasing it at a much greater, much lesser values, which is good. And we are plotting this best objective function value in each iteration versus number of function evaluations, not the number of iterations once again. So if you look at the population diversity, you will see that the population diversity is also preserved to a large extent by the spherical search. In case of DE, since DE uses a greedy selection mechanism, DE is very much susceptible to quick convergence and premature convergence, which you can see here right away. Quick convergence or premature convergence means most of the solutions will very quickly enter into a small region in the search space. That is what is happening for D. PSO doesn't have an explicit selection mechanism. That's why PSO's population diversity can remain preserved unless the functional landscape is very deceptive. But the spherical search keeps the population diversity to the maximal extent because of this hyper-spherical search style adopted by its solutions. Okay? So spherical search also has a number of parameters. There are 30. So let's just analyze the parameters. So sorry, 3 parameters. Spherical search has 3 parameters. If we look at these 3 parameters, what are they and how do they affect the search? That is also very important to understand the algorithm, and maybe for devising other algorithms on the same philosophy. So you see, let's take a set of 30 test problems with 30 dimensions, each in 30D from the IEEE 2014 benchmark suit. And if we do the Wilcoxon's signed rank test at 0.05 significance level for comparing the algorithms, these are some algorithms. After the same, so these are the experimental results. We are varying this small c to different ranges. We are finding in how many cases. Plus means in 21 cases with c equal to 0.2, SS was greater than SS with c equal to other values. These are the results. Based on the results, we see that the step size parameter could be very well between, at least for this benchmark fruit, P could be very well between 0.5 and 0.7. R, which determines the rank of the projection matrix, R could be half of the number of dimensions, and P could be 0.1. So these are the 3 parameters, and these are the parametric sensitivity analysis. Parametric sensitivity usually means you will choose different values of these parameters and you will run your algorithm at these different values, and you will show us the result. You will just compare the results and pick up the best hyperparametric configuration. Parameter setting is a dilemma for any evolutionary computing algorithm or any data heuristic. How to strike a proper setting? What we could do is see the adaptation of SS parameters are very easy. At each iteration, the rank projection matrix the rank of the projection matrix is governed by Ri. So we can choose this Ri as a binomially distributed random number because it's like whether a diagonal element will be 0 or 1. When you toss a coin, whether you get a head or tail. That is called a Bernoulli trial. And the number of successful Bernoulli trial, number of heads out of 100 such Bernoulli trials is usually a what? It is a binomially distributed random variable. So we can use binomially distributed random variable here, and we can choose Rik as a binomial random variable with parameters d, number of trials, length of the diagonal, and L. Probability L would be selected where actually this L1J is the element from memory matrix L. J is randomly chosen from the column of memory matrix L for every I independent. And in this memory matrix, you could actually put those values of the parameter for which the SS was successful previous. That is called it's the record of the previous success. And Rik is a Cauchy distribution. So Rik is truncated. Whatever value it gives, it will be truncated to 1, within this. The step size control parameter Ci is generated from a Cauchy distribution of mean L2J and standard deviation 0.1. So the memory matrix contains two rows. One row for the previously successful number of previously successful rank values for the projection matrix, and the previously successful means by using those rank values and those CIs, the trial solution YI that was generated was better than the other solution itself. So CI is the state size control factor. CI is the Cauchy band, and CI is truncated to 0 and 1. At the end of each iteration, so we can also do something like that. At the end of each iteration, calculation of the learning values LR and LC are required. For this purpose, we keep two vectors SR and S containing the R and C of successful trials respectively. And LR and LC could be computed. This is just these equations may look somewhat costly to you, but this is basically saying that you are taking the length of the vectors and just taking some weighted combination of the lengths of these vectors. So that's what we are doing. This kind of a labor mean we are using, and then so this was some kind of success-based parameter adaptation for the spherical charge. And after this, the performance was even more improved, and we compared against the very recent winners of the CEC competition, starting from CEC 2018, 17, 14, and 13. Of all the 10D, 30D, 50D, 100D problems, and we could see the total Friedman rank compared to the other winners is very good for SASS. In fact, for this set of problems, it always attains on the bound constant values, it is always attaining a good rank. Not always the top rank, but still it is quite commendable, even these recent, because these are all winners of the previous year's CEC competition, and this is a new algorithm. So you see, if we now test on the Cs, especially for the real world problem, SS gives us really nice results. If we compare it on the CEC 2011 competition problems, and if we use the self-adaptive version, then the FR stands for Friedman ranking, which is a statistical test. We see SASS always comes up with the top rank. GA-NPC, by the way, was the multi-parent crossover-based genetic algorithm, which was the winner of the earlier CEC competition, CEC 2011 competition. So we see that Now, coming to constraint optimization, optimization can come up with, apart from the upper and lower limits of each decision variable, it can come, which are called bound constraints. Optimization can also come up with other nonlinear constraints, non-convex nonlinear constraints. Just as an example, let's look into the heat exchanger network design. One of the major components in a chemical process. The heat exchanger network has the task of integrating the hot and cold process streams in a process in order to reduce the amount of heating and cooling utilities that are required. This is basically a non-convex and non-linear constraint problem. And the objective is like a set of hot streams that must be cooled and a set of cold streams that must be heated are given. There is a fixed heat capacity, flow rates, and inlet and outlet temperatures are specified for these streams. The problem then is to derive in an automated manner a heat exchanger network configuration that minimizes the investment cost of the heat exchangers, while so it doesn't only minimize the investment cost of the heat exchangers, but also tries to take care of using minimum utility cost and minimum number of heat exchanger units. So this is a non-linear problem, non-convex, and has several local units. This is the problem. This is kind of description. If you convert it into a problem, it looks like this. The example heat exchanger network design problem is like this. You have this function to minimize, but at the same time you have 7, 8, 9 equality constraints and these bound constraints, all equality constraints. These values must be maintained. And along with that, you have these restrictions on individual variables. The upper and lower limits are not the same. So we created very recently a test suite of 57 such real-world constrained optimization problems, which are of very complex nature, and all of which are very real. That's the problem. Sometimes you just generate an algorithm and test it on hypothetical functions. That's not enough. That's why we come up with a set of 57 real-world constrained optimization problems. And this set is available under this paper. If you look at the paper, you can get all the GitHub links and other things, where you could have codes for all the problems in MATLAB, Java, Python. These problems are shown to capture a wide range of difficulties and challenges that arise in real-world, real-life optimization. So, and if we group the problems, you will see that the industrial chemical process, there are 7 problems from industrial chemical process, mechanical engineering 19 problems, power systems 11 problems. So that's a kind of histogram of the problems. And the number of decision variables vary from 2 to 158, number of equality constraints from 0 to 148, number of inequality constraints from 0 to 91. You see the wide range of complexity of this problem. Now we adopted spherical search for the constrained optimization as well. Spherical search is a, so what we did is we took less number. So spherical search usually, why we choose it? Because it usually exhibits these characteristics once again: rotational invariance, less number of parameters, high diversity during the search is maintained, and so on. And here we use a self-adaptive parameter tuning procedure and the popular epsilon constraint selection scheme. Epsilon constraint selection scheme means each of the equality constraint is converted into an inequality constraint by using an epsilon relaxation on their margin, and thereafter a gradient-based repair was integrated within the framework to efficiently the constraints. So we ran it on the IEEE CC 2020 test suite. So the same set of problems were used in the IEEE 2020 competition also. Competition on real-world constraint optimization problem, where these were all the participants. You can see the participants were mostly from differential evolution, then this cooperation biology. These are other people's papers. covariance matrix adaptation, CMAES, these were the participants, among which SASS ranked the top. Okay, and this is the actual competition result. Similarly, we applied it for power flow problems in islanded microgrids. I'm not going to discuss it in enough detail. The power flow problem is a very interesting problem where we try to determine the bus voltage magnitudes and phase angles in order to guarantee a steady performance of the power system. And the purpose is to plan ahead and account for various hypothetical situations. Power flow analysis. So this is an example of a 3-node point. I'm not going into the details of this. The slides will be provided to you so you can see. Power flow analysis is a typical optimization problem, and we just used, so it looks like this. This is the objective function for the islanded power microgrids, and this must be minimized subjected to such equality constraints and such bound constraints. So this is the exact mathematical description of the problem. So we used 4 of the very current algorithms, one of which is from our group only. This last one, this is an IEEE access test in 2021. This was a DE approach. Then we used SS with some modifications, and then we see that for the ill-conditioned test systems and for both the ill-conditioned faculty lines, SSNR gives us the best performance. NR is a constant handling mechanism, and it gives us the best performance always. Of course, the codes are also available for this particular work, which is going to be published. So, in a nutshell, what we have gathered is when we, even if we are talking about no free lunch, when we present an algorithm in original form, we must compare it with the most competitive algorithm. We must not avoid that comparison. If our proposed algorithm is achieving good rank within 1 and 2, top 1 and 2, on the compared algorithms, then only publisher will actually. And when we are proposing a new algorithm, see, we have compared, I showed you that we have compared against all the DEC competition winners. Some of the GECO winners also were included. So we are comparing against the current state-of-the-art best known algorithms which have participated in certain public contests and which have won those contests. Nowadays, it's not like that. You propose an algorithm and then you compare it with ESO, DE, GA, all of which were proposed more than 30 years back from now, at least 25 years back from now. So it's not like that. When you propose an algorithm, you must compare it with the currently best known set of algorithms. You should not say, okay, I will not compare with the best variants because my algorithm is the original algorithm. So why you are keeping it in that form? You should modify it in that way so that the currently best known algorithms should have a good competition. First, second thing is you should also take the framework of the algorithm, impose it on the other algorithms, and see how the performance of the other algorithms could also be improved by the use of spherical search or similar philosophy. In our case, in your case, it could be different. You should test your algorithm on diverse optimization scenarios, like when a lot of constraints are present and so on. You should not test it on just one single scenario. That's why, and you should also very clearly tell us, what are the control parameters, what are the effect of these control parameters on the performance of the algorithm through a systematic parametric analysis. Thereafter, you can write another paper on how to do this parameter adaptation and so on. But these are the usual norms when you try to present a new algorithm. So I will be concluding now. Coming to the conclusion, I presented some systematic approach to do spherical style search, population-based stochastic algorithm domain. That's the domain of meta heuristic. And we call this total approach as SS. SS is basically a framework. This framework could be adapted to many other algorithms, and the effects of those on those algorithms could also be studied. It can be easily, the SS algorithm in itself, it could be very easily adapted for non-linearly constrained and multi-objective optimization. Both the situations we have tested, and two papers you can see here, they are in order, very recent reports. SS renders itself to commonly used parameter tuning method. Commonly used means nowadays we always, whenever we have some free parameters of our algorithm, we do not let them go just hanging in the sky. We try to adapt their values based on the previous success of the previous settings. So that is the parameter tuning method. SS easily renders itself to such parameter tuning. And of course, different trades-off between explorability and exploitativeness could be attained by controlling the rank of the projection matrix. In fact, low precision projection matrix, which is the topic of this first paper listed here, could improve the computational time and could give us even better results sometimes. Because we have, of course, certain, you know, random components also. So this is it. This algorithm is just on the ground, and we have made all the codes and other things publicly available. Nowadays, reproducibility is a very big issue. When you are claiming some result or you are writing a paper with some, this sort of empirical experimentation, it is your duty, in fact, to make all the codes and all the results duly available in public platforms like GitHub, ResearchGate, or similar platforms, so that anybody sitting in another part of the world would be able to reproduce the results that you got. Otherwise, there is no meaning of research. So with this, I would like to conclude. Thank you very much for your kind patience.